Hello everyone, and welcome to our Arsenal talk about Tracee, a Linux runtime security and forensics tool using eBPF. I'm Yaniv Ajman, the creator and one of the maintainers of Tracee, and with me is Roy Cole, who works with me on this project. We're both security researchers at Aqua Security, and we're excited to be here and share this tool with you. So we'll start by presenting the motivation for creating Tracee. Then we will give an overview of the project. We will go through some example and use cases and present several demos. The first demo will show a new feature recently added to Tracee that enables us to capture network packets with process context. We'll then show how Tracee can be used to detect privilege escalation made by a real kernel module rootkit. In the last demo, we will analyze a real multi-stage malware which performs dynamic unpacking and fileless execution. We'll finish the presentation by showing some of the future direction for the project. Okay, so let's talk a little bit about the motivation behind writing Tracee. We wanted to be able to analyze potentially malicious container images. But unlike a regular process, which can be analyzed with traditional sandboxes, a container has a full-blown file system, its own life cycle, and is running on its own Linux namespaces. After investigating some real attacks found in our honeypot, we realized that attackers are leveraging static evasion techniques, exactly like they're doing in other operating systems. So we understood that static analysis is just not going to be enough. For example, we saw a base64 encoded payload inside of shell script, such that the payload would be extracted and executed only at runtime during the container execution. And that's enough to bypass most pattern-based AV scanners. So we need to find a way to trace the container execution in order to find and capture suspicious behavior and artifacts in potentially malicious images. One last thing that motivated us to write Tracee was the desire to explore the relatively new and exciting eBPF technology, which we thought might fit for our needs. So after we understood what we were looking for, we started to look for a suitable way to implement this. There are several technologies in Linux for tracing a process or a group of processes in runtime. ptrace, for example, is used by strace to trace system calls performed by a process. But as you can see, it has bad performance and can only trace user space programs and not the kernel. Library injection is done by tools like Frida, where the injected library is part of the address space of the trace process. This method is easily detectable as the trace process can perform integrity checks on its own address space, as well as manipulating the injected library data. With kernel module, it is easy to hook and trace functions from within the kernel. Loading a kernel module could have been a good option, but not all environments allow to load the kernel module, and a single mistake in it can crash the whole system. This is where eBPF comes to the picture. It allows us to run code in the kernel in a safe way. eBPF is a relatively new technology, with which it is possible to trace almost any event in the system. Eventually, eBPF is a virtual machine running in the Linux kernel, which has its own instruction set and registers. Before any code can run in the BPF virtual machine, it first gets verified by the BPF verifier, and if passed, it gets JIT compiled to native code. An eBPF program can be written in user space just as a regular C program, but has some restrictions. For example, it is necessary to use special BPF helper functions to do trivial things, such as reading a pointer to memory. After loading a BPF program into the kernel, it can be attached to an event such as a kprobe, tracepoint, or a network event. When such an event happens, it triggers the BPF program, which can interact with the user space using ring buffers or maps. This effectively means that we can attach our own programs to points of interest in the system, and these programs will be triggered in an event-driven fashion. So what is Tracee exactly? Well, Tracee is a runtime security and forensics tool for Linux. It is using the Linux eBPF technology to trace your system and applications at runtime, analyze collected events to detect suspicious behavioral patterns, and capture forensic artifacts. It is composed of Tracee BPF, which collects OS events based on some given filters, and Tracee Rules, which is the runtime security detection engine. Tracee BPF is a system tracing tool with specially added tracing and forensic capabilities, focused on malware-related behavior. Here you can see a partial list of events that can be traced with Tracee BPF. In the full list you will be able to see all the system calls plus some other events. These other events include internal kernel functions, such as LSM hooks, and also some specially crafted events, as we will show later. One more thing that you can see here is what we call sets. Using sets, you can trace a group of related events, such as all the file system events or network events. This can be helpful when you know what you want to focus on and remove any other clutter. Tracing LSM hooks has several advantages over tracing system calls when capturing certain events. One advantage is avoiding time of check to time of use attacks when tracing pointer arguments. For example, tracing the path argument of the execv system call is exposed to a race condition, where one thread of a malicious process can call execv while another thread tries to change the path given to the execv as a pointer. We may read one value when tracing the system call, while eventually the kernel will execute a different binary as a result of this race condition. Using the security BPRM LSM hook, on the other hand, we can read the internal kernel data structure and get the effective file name that was given to the kernel as an argument. Another advantage of hooking to LSM hook is that we can extract the absolute file path given to the system call, even if only a relative path or a link were given. Tracee BPF includes advanced filtering capabilities so that you can focus on the things that you want to trace. It is capable of tracing all processes in the system or a group of processes according to some given filters. In the first example here, you can see that we can start Tracee with a filter telling it to only trace newly created processes. We then call the ls command. Tracee gives a timestamp of the events, the user ID of the process that triggered the event, the command name, process ID, thread ID, return value if applicable, and then the event name and its arguments. The second example shows how we can start Tracee and tell it to only capture events from newly created containers. With this filter, processes which do not belong to a container will not be traced. Instead, when a container is started, for example with Docker, Tracee will detect that and start tracing all of its processes automatically. In the last example, Tracee is started with filters that tell it only to trace bash processes or processes spawned by bash. We can choose not to trace specific events, for example close and access in this example. Tracee has more filters, which allows you to focus on what really interests you. One example is argument filters that will trace an event only if an argument equals something. And of course, there are even more filters to play with. Other than tracing, Tracee BPF is also capable of capturing forensic artifacts automatically for later investigation. One example is capturing files written to disk or memory. To do that, we give it the capture flag, telling Tracee to capture file writes. In the first example, we also use filter as we don't want to capture all of the files written, but only those written to the pseudo terminal. So we just filter using devpts. Below you can see what Tracee captured. In the output directory of Tracee, you can see a file with a name matching the device ID and inode number of the file that was written. Printing the file content, you can see the output of the ls command, exactly as was shown in the terminal. Although there were several writes to devpts1, as you can see from the VFS write events above, only one file was created, which contains the whole content that was written. As you can see in the output of Tracee, the VFS write events were triggered by bash and ls. given the absolute path of the written file, as well as the device ID and inode number. Using this data, we can correlate with other events, such as security file open and security BPRM check, as you will see next in our demo. Another artifact which can be captured using Tracee BPF is an executed file. Using the capture exec flag trails Tracee to save all the files that were executed since Tracee was started. In the above example, you can see the security BPRM check event, which happens every time a binary is executed in the system. We use the less and ps commands in the background, and as you can see, these executables were saved to the Tracee output directory. One more thing that Tracee can capture is the content of a dynamically loaded binary. In the above example, we used the file which was packed with the UPX packer. In addition to using capture mem, we ran Tracee with what we call security alerts, to get alerts when a memory protection is changed in a specific way. There are 4 types of alerts that may be triggered, depending on the flags given to mmap and mprotect. The idea is to try to find memory regions that were mapped with write plus execute permissions, or change permission to such value. In normal programs, text section will be marked as executable, but not as writable. Also, data section will be set to writable, but won't be executable. If we see both execute and write flags, it may indicate that the program is trying to dynamically load binaries into its address space. For example, a packer will store its data packed in the binary, and unpack it into a memory region that must be writable. It then will want to execute code from it, which will require it to set the memory region as executable. Usually, the packer will not keep the memory region both executable and writable, as this may cause the program to crash on an invalid write, or even be detected by anyone searching the procfs for write plus execute memory regions. We use this fact to save the binary data written to such memory region when protection is changed and write permission is removed. We know that the data was written and we save it to disk, giving the saved file name as part of the alert output. Having the saved text section captured, we can then perform further investigation on it. A new capability of Tracee is capturing network packets with the context of the process. This capability is still a work in progress, and there are still a lot of new features to build around it, but it works and you can already play with it. This allows us to use any of the existing filters of Tracee to capture network packets of only the traced processes or containers. Let's move on to Roy, so he can show us how this works.
Thank you, Yaniv, and hello everyone. So let's see this cool new feature in action. Let's say you got a malware sample and you want to dynamically analyze it. Now, if we're talking about network analysis, then traditionally you would run TCP dump in the background and then start the malware process. TCP dump has no context of the system processes, so the resulted pickup will contain every packet that goes through the network interface. This will cause the pickup to be very large and full of unrelated noise, and this leads to longer and more difficult investigations. Let's see how we can use Tracee in order to filter on the process, and we'll also run TCP dump on the background just to compare. Now, in this example, I'll just show the wget process instead of a real malware sample, just so the pickup will be cleaner, but the concepts are the same. So we have the sample ready to run. Let's now run Tracee. So we'll use the debug flag because we want to see the networking feature debug messages. And we want to trace process wget, so com name wget. And we want to capture network interface in P0 S3. So Tracee is ready to capture, and let's run TCP dump on the same network interface. We are ready to run our sample, and wget finishes very quickly. Let's go ahead and terminate TCP dump, and let's terminate Tracee. And as we can see in Tracee's output, we see the debug messages that we captured packets of these IPs and these ports from the wget process. So this looks very good. You can also see the pickup itself, so let's open that. And as we can see, the pickup is quite small as we expected because wget doesn't do much. We see DNS request to google.com and we see some TCP and HTTP packets, so this is very nice. And we can see the TCP dump pickup, and we can already see that TCP dump captured 300 and something packets, while Tracee only captured 32 packets, only from wget. In TCP dump we can see some TLS packets, and we have a DNS request for mozilla.com, which is totally unrelated. So as you can see, this feature is really exciting, but it's a work in progress. If you notice, the pickup doesn't yet have the TCP SYN and TCP SYN ACK packets. This is related to how things work under the hood, but we're working on resolving this. We also have to add support for more protocols like ICMP because we currently only support TCP and UDP. So there's a lot more to do and more features to build around this new capability, but this will be very nice and you should stay tuned for the latest updates.
Okay, let's move to talk about Tracee Rules. Tracee Rules is a rule engine that works mainly on events generated by Tracee BPF. Its purpose is to enable detection of suspicious behaviors in the system. The rules engine job is to get the stream of raw events from Tracee BPF and dispatch each event to any rule that requires it. Each rule evaluates the dispatched event and decides whether there's a hit or not. The rule can also return a value. For example, if we detected a malicious file based on some logic, we would at least want to return the file path. Tracee Rules currently supports writing rules with Rego or Golang. Rego is a policy language by OPA, which is Open Policy Agent. It aims to become the standard of writing policy rules, and it should make it easier to write them. Okay, so now that we know what Tracee Rules is, I want to show you a really nice use case that we have. So this is a Rego rule for detecting privilege escalation. Let's go really quickly over the rule structure. So we have the package name, which should be unique across different rules. Then we have the import for some common helper functions. Then we have the Rego metadoc, which is just metadata about this rule, like the rule ID, version number, the rule name, and etc. And then we have the event selectors, which essentially tells the engine that this rule works on the CommitCredits event from Tracee. Lastly, we have Tracee match, which is the rule logic. But before going through the logic, I want to show you the CommitCredits event. So CommitCredits is an inner kernel function, and as we can see here in the kernel sources, it is responsible for installing new credentials upon the current task. So this means that this function can change the process credentials. So it's a nice place to hook. Now the CommitCredits receives a new struct cred, and this struct holds the information like the new UID, GID, effective capabilities, and more. And now we can run Tracee just to see how the CommitCredits event looks like in Tracee. So for this demo I will use the diamorphin rootkit. And diamorphin is a kernel module and it has several commands. One of these commands is privilege escalation. So if a process sends a signal 64, diamorphin elevates the privileges of that process. So let's install diamorphin, and now diamorphin is enabled. And we can also run Tracee, and we want to trace the CommitCredits event. So now Tracee is ready. And we can spawn a new shell and just run whoami to verify that we are the Ubuntu user. And now we can send the 64 signal to any PID that we want. So we do it, and let's run whoami again, and we see that it worked. We are now root as opposed to Ubuntu user. And let's go back to Tracee to see how this event looks like. So we have the CommitCredits event on Bash, and we can see that old credentials of Bash were 1000 for the UID and 1000 all over. So we have GID, UID, all for the Ubuntu user. And then we have the new creds, which is 0 all over, which means UID 0, GID 0. And that means that Bash elevates privileges from the Ubuntu user to the root user. So now we can go back to the rule logic. So we have Tracee match, and in order for this rule to hit, we want Tracee match to be true. And in order for Tracee match to be true, every statement in this block should be evaluated to true. So we have this check. We are checking that we are working on the CommitCredits event, and this is just a variable assignment, and we have some more statements here. So we take the old cred and the new cred from the Tracee event, and what we want to do is take the new UID from the new cred and check it against the old UID and the old saved UID, so we can verify that the new UID is indeed new. So we do it in these statements. We check that new UID is different from these values, and then we want to check that old UID wasn't 0, because if it was 0, then there is no really privilege escalation if you are root to begin with. So we check that old UID is different from 0, and we check that new UID is 0, and that means that we have a privilege escalation from non-root to root. So let's run this use case again, but this time we will use the Tracee rules. So we pipeline the events into Tracee rules, and Tracee rules read the events from the std in. So we see the Tracee rules is up, and it's loaded some signatures. If you recall, our signature is number 61. And let's kill this shell and spawn a new one. So we can check again that we are the Ubuntu user. And now let's send the 64 signal to any PID that we want. And again, who am I, to see that it works. And we can see that Tracee rules has a detection for privilege escalation from the Bash process. So this is very cool. Now I want to show you how we can use Tracee in order to analyze a suspicious container image. So it's a good idea to start Tracee with security alerts on, because this is a suspicious workload. And because this workload is a container, we want to trace only new containers. So Tracee is ready. Let's go ahead and run our container. And we can see that Tracee generated a lot of events. We can see something weird here. We have a process name number 3. And if we scroll up, we can see something that looks like base 64. And so this is too noisy, so it's probably a good idea to run this all again, but now we want to run it with filters on execv and security BPRM check. Security BPRM check is an LSM hook for running processes in the system. So Tracee is ready with these filters. Let's run our container again. And this time we can scroll up very easily. We can see very easily that in ETSH is the entry point of the image. We can see that in ETSH runs sbin after it starts. After that we can see that sbin executes a file descriptor number 3, which may explain why we have a process name number 3. In the security BPRM check that matches the execv, we see that the path name of this process is memfd. So we can understand we have a fileless execution here. And if we go down, we see we have memprot alerts. This is due to the security alerts on. So we have a protection change from write and execute to execute, so this is pretty suspicious. We also have a base 64, probably decoded using the base 64 binary. And eventually we see this queue process, and after that we see that the queue process generates memprot alerts, and that's about it. So I think the really interesting thing here is the cube. If we look at the execution of the container, we see that it can't run on this architecture because of the cube. So our end goal here is to get this cube process and to further analyze it using a reverse engineering program or with antivirus. So how do we get it? Let's run Tracee again, but this time we want to capture these artifacts. So we want to capture the VFS write to this memfd, and so we can filter to this memfd with the path name argument. And we also want to capture mem, so this memprot alerts, if this is some sort of unpacking, we can capture the artifact. So Tracee is ready again. Let's run our container once more. And this time the output looks very familiar, and the only thing that's different here is this VFS write. We see the actual write to the memfd that later on gets executed, and we see that the VFS write is performed on device 1, inode number 1231600, and if we scroll down, we can see that the cube memprot alerts is saved by Tracee into this file bin6126. So let's go to the Tracee output directory. So here we can see that indeed Tracee saved us the execution artifacts. We see the write artifact on device 1 on the same inode, and we also see the cube unpacking payload. So this is actually the final payload. We can take it and further analyze it with the reverse engineering like IDA, or we can send it to an antivirus for evaluation. But this is very good. So let's recap what we had here. So we had a malicious container image that is using fileless execution in order to go undetected by static analysis methods. And we see that the final payload of this container is an execution of a packed binary. So we see how Tracee helps us to quickly understand what this suspicious workload is doing, and also how we can capture forensics artifacts from different stages of the execution. Okay, so now that we've seen the power of Tracee, let's talk about our future plans. So we want to add more network related features like supporting more protocols, allowing network oriented filters, and more. The next thing on our roadmap is supporting BPF LSM programs, which will enable us to not only detect malicious behaviors but also enforce runtime policies. And as a future research, we want to be able to detect rootkits and container escapes using Tracee. And of course, you are welcome to visit our GitHub page, use the project open discussions, contribute, and if you like it, give it a star. Thank you very much for being with us in this talk, and stay tuned for future updates on the project.